All right, we're going to go ahead and get started. If you are having trouble signing in, come talk to me. The Wi-Fi is terrible. This is a pervasive problem throughout the quarter. Okay, so this is our last guest lecture of the quarter, our penultimate week also. I will be sending out the exam study guide today for exam number 2. And yeah, I'm not going to take any more of our speakers' time. So I want to introduce Keith Muller. Keith is currently in residence at the Halijolu Data Science Institute, and he is on loan from Teradata. He was formerly the CTO for Teradata, and he actually taught in ECE here. Was it just EE?
Yeah, actually it was in CSE.
CSE, okay. Here at UCSD, and actually Tanera Halijolu counts him as one of his favorite professors while he was here. And so he left us for a while to go and do big things at Teradata, and now he's back for a little bit. So everyone, please welcome Keith Muller. Thank you.
Okay, I'll try not to go too quickly. I have a tendency to go a little fast. But if any of you have any questions, slow me down. So I'm from Teradata. I've been there for a long time. If you don't know Teradata, I'll have to give you the company line. It was founded in 1979 up in El Segundo. It's currently headquartered in San Diego. It really started off as a database company, and then over time transitioned to doing data analytics and data science. And a lot of our customers that we have do intensive amount of data science as well. We're a mid-cap size company. There's 10,000, more than 10,000 employees. The interesting thing is there's 5,000 industry and consultants, and they're an interesting group of folks. They actually work with the customers and they actually deliver the solutions. So they very much, what we're going to see today is stuff that they have worked on, and some of these things I've worked on as well. But everything we're going to talk about today is real. Nothing's looking to, this could happen. Everything here we're going to see today is real solutions that really exist, that really make money. So one of the things I want to try and get you to do is, this room's full of data scientists, and I want you to stay here because we need data scientists. We just can't hire enough of them. So I've been there since I started working there as a consultant from 1984. And in about 1994, I became an employee, and I was the chief architect or the CTO for about 20-something years in the platform engineering area. I'm an electrical engineer by trade. Partway through my career, I decided I didn't want to do microprocessor chip design, so I went back, got a PhD in computer science, played around while I worked at databases at Teradata for a while, and where I'm very much envious of you guys is I didn't pay enough attention to my math classes, so there's periods of times where I'm not really a data scientist. I will hire them and help me out because I can only go so far. So I'm a little envious of you guys getting a way better training in this area than I ever had. You've used Teradata. I can guarantee it. There is not a person in this room that hasn't used Teradata, didn't know about it. If you got I'm not supposed to talk about customer names, but if you have an iPhone, for example, the back end, you're using Teradata. I mean, if you fly an airplane, almost every airline, the routing, the logistics, if you ship a package, any package, UPS, FedEx, all those people are all Teradata customers, and all in the back end. So where we're not well known because we're not a consumer company, we pretty much drive a lot of this back end industry. So there's a byline that says invest in answers. So I have 2 goals here. I want to talk about how a practicing data scientist works in industry and really what is the value and how it's determined. And this byline, I really hate marketing lines, but this is the current one we have. It's called Invest in Answers. It's actually the first one in, 25 years or so that I actually like. And really what the whole point here is trying to find the value in data. Too many of the data scientists, they come to work and they get the data and they try literally every algorithm, every analysis thing they can do, they just throw the book at everything, and they should be stepping back and thinking, what the hell am I doing? What is the value? And sometimes the value is not a whole bunch of data science. Sometimes it's a combination of business sense. So we'll talk a little bit about that. We're going to take a look at, I picked one area, and I picked sensor data. And really why I picked sensor data, this is my opinion, by the way, is that data has to come from somewhere. You have to operate data. I see, and we'll talk about a little bit of trend data, I see the vast majority of data applications being created by data that came from a sensor. And I'm going to use sensor in a very broad term. And that's basically, and we'll talk a little bit about what I mean by a sensor. I'm going to show some case studies. So we're going to do a little bit of introduction because I don't know your background. I want you to at least get up to the level so when I talk sensors and I talk, events and synchronous data flows and things like that, you have an understanding what it is. But then we're going to take a look at how did companies use data science with sensor data to solve some really cool problems. And I tried to pick a little bit of history as well as that all of them are relatively cool. And then if we have time at the end, we'll do some questions. Okay, so when you're in industry, the very first thing is, do you understand the problem, right? And you got to learn both the business and the engineering or the technology. So the most effective data scientists I know always work with what is the business problem I'm trying to solve and what is the technology environment I'm working with? Where did the data come from? Because if you do not understand this, you can start analyzing the data the wrong way and come up with garbage. And so that is not really what you do. You step back and as I said, understand the parts. And you're going to have to work with engineers, business people, luckily, usually, hopefully not salesmen, and people in finance, because one of the other things is, part of the thing about the value is understanding the economics. The data science problems you solve will be based on the value of the science itself and the ability of the company to wanting to pay for it. So the problems you are solved is very much dependent on the cost of the technology to implement that. And one of the things we'll talk about today is a data science solution that sat on the shelf for 9 years. We knew how to do it. We couldn't make it work because the technology wasn't there and it wasn't cost effective. It deployed about 2 years ago. What is the value of the answer over time? Will it still be valuable several years from now? If you're going to analyze, you're going to make an investment, is it going to be valuable over time? Is there improving cost, improving efficiency? Well, let me give you an example. Say you'd work on an algorithm, and you work really hard, and you go to it, and you say, and I could have done this when I was in grad school. You go up to your advisor and say, hey, damn, I've got this cool algorithm. I improve the performance of finding the results. The result of a find of this analysis is 1% better. And everybody go, that's not useful. No one's going to be interested in 1%. Well, let's think about this. Let's talk about the business value. What if that 1% was reducing the travel time of a container ship? And all the container ships in the globe, and at least for their company, would have a 1% in production and travel time. Container ships today burn $16 billion a year in fuel costs. So I now save 1% of $16 billion. That's $160 million. I think that's a reasonable solution. So the whole concept is you have to put in perspective of what you're trying to solve. And there's a lot of cases where you're going to see big input costs that have with little gains are always worth the thing, where if you were sitting there and looking at it in the background and say, oh, I only got 1%, why did I bother? That's not the right way to look at the problem. Okay, some more here. What happens if you're successful? Okay, I've got this great model. I got a sample data set size. I modeled it. I looked at it. I got a solution. And I want to deploy it. Uh-oh, it really works. My solution, will it scale? It worked really good when I have, 500 data samples. What happens when you have 4 billion? Can your solution work in real time, or whatever time length you have? Again, we've had many cases where we figured out solutions. You built the data science model. You actually had the algorithms working, and you couldn't complete it in time. There's a really great one today. They've been trying this for years. Weather, right? They've been trying to predict the weather. It takes like several days to predict the weather, which is not particularly good. They're getting better with, hopefully technology will fix that. But that's a perfect case. Is you will be successful. Will it scale up? In some cases, will you also have to scale down? So you have to think this through. Just don't come up with a solution. Look at how it will scale. And that also includes, and you get a lot more data sources. You get a lot more users. You know, you work really great on your desk. You get 100,000 users. Like, imagine if you had built a little system that worked with one or two people, and you became your next Amazon. You suddenly had millions of users, and the whole system fell apart, and you couldn't sell anything. You go out of business. So you have to think these things through. The other thing is technology will screw you up. It's going to change it. Sometimes it'll make your answer no longer valuable anymore. It will actually change the value of the answer. Sometimes it'll make you have to go back and think about it and say, I better look at my implementation and decide I better approach this from a different way. Because the technology has made my approach inefficient. There's a better way to do that. Always, always look at technology going forward. The single most important thing that I learned when I was a grad student, the one thing that's for 40 years and being doing this, the one thing I learned and it would save me every time was to look forward. How will technology screw me up? Look, not today, don't look in the future and say, what could happen? Will the cost get better? Will performance get better? Will there be new ways to solve this? Always shoot for tomorrow, because I see too many people design for today, and when they finally get done, the thing isn't worth anything. So it was the hard thing to remember, but of all, I can sit back and the best advice I have ever gotten was to look forward. Okay, and as a data scientist, you will be judged on the value, not the cool algorithm, but the value of the solution. I have this 1% algorithm, and I save the company $160 million a year every year. It's a recurring revenue stream. That guy got heavily rewarded. Okay, so sensor data. Now, sensors observe something. Heat, light, gas flows, temperature. There could be a video camera. It could be a GPS system. It could be a barcode scanner, but they observe something in real life, and they convert that, whatever it is, to some ugly looking signal that they put into what I call a sensor subsystem. Now, you can spend an awful lot of time. There's a whole set of things called signal processing and a whole bunch of other things where you can worry about looking at ugly signal and trying to figure out where the data is in that electrical signal. I kind of throw this off the scope. As I'm watching over time, the subsystem, which consists of the sensor, is getting more intelligence, so less and less of that processing requires everybody to understand. Now, there may be a data scientist involved in understanding how to pull the data out, but it's not the vast majority of the system. So having to deal with low-level signals over time, I'm seeing less and less. And we'll get a little bit more into that. So you got a sensor subsystem in there, and you're converting electrical, physical, and sometimes the sensor system will do a little bit of data science, and we'll show you some examples of that. It ends up in the computer, and it ends up with storage, and the data that you're applying has to be, that you're actually picking up, you apply your algorithms over there. And that's kind of a big picture. I want to make sure everybody's on the same page here. All right? Sometimes sensors are in the same system, but more common is that they're physically separated. The sensor is someplace else. So there's a communication, let's get this going. So there's a communication network up here that connects this sensor to this computing system, and that's going to be something you have to consider. And we'll see some examples of that as we go forward. Now, here's a whole bunch of cheap sensors, and I just looked at these. These are the kind of things you can use with a Raspberry Pi if you're mucking around on the side. But they're nice examples. Everything are relatively inexpensive here, but what you often end up doing is when you get into real world applications, this sensor is tied with some compute hardware. So often it's an embedded device, and it has a higher level interface, and it produces some kind of data stream, and you don't really have to dig the signals out. And we're going to talk a little bit about some of these, but you can see gyroscopes, infrared, ultrasonic IRs. These are all cases of very simple sensors. These things are all under $10. So what am I trying to get to you? Sensors are cheap. which means they can be easily deployed, and if you get them everywhere, you're going to generate a whole ton of data, all right? And you're going to have to deal with it. As of course, higher value sensors, they just have more compute power and they may have more sophisticated sensors, but again, it's the same model. Now, let's talk an example. Let's talk about retail and a barcode. This is the earliest sensor that I've ever, in my entire career, I really ran into. This is the case where these are the barcodes they put on the back of products, and what they do, they have a scanner, and when these first came out in 1980, things were about $60,000, and you kind of really saw them looking something like that. And you went through a store, and this was revolutionary. It cut down people, bad price checks, bad other kinds of things. It also created a data stream that says, this item has left the store. And it automated it. So now you created a data stream, and this is what we'll call an event data, but it creates data stream that says, and you get something like that. We'll talk a little bit example. Now, another one of sensors I'm going to talk about, and these are ones we're going to talk about today, is geospatial. And geospatial sensors they were about $3,000, and if you really couldn't find out the cost of the sensor back then, but the unit cost about $3,000, and I figure the sensor was probably about $1,000. They're down to about $10 module today, and you got the electronics here in this part, and then this is the antenna. And of course, the antenna is the one Achilles heels to these kinds of sensors is the fact that you really have to have a clear view of the sky. And we're going to talk a little bit later about problems in doing this stuff. But the primary function is location. This produces a stream of data. And it says, I'm at this location, it's using satellite data. You can also use it if you take snapshots of this sensor over time. You can calculate speed, acceleration, things like that. But it also gives you XY coordinates and vertical, and it gives you latitude, longitude, and altitude. And that's really what this spits out. But you can process that. So you can create graphs and charts, and you've probably all seen that in cars and handheld GPS systems on your phone, where you can create how fast you're walking based on the change in the GPS data. It's very heavily used in farming. We don't have time, in that time I can't talk about the ag tech, which is really cool, but this is these sensors are popping up everywhere. At $10, they're cheap. So any application that needs to be aware of where it is that can move, you wouldn't put a GPS sensor in something that's nailed to a wall, but if the thing can move and you care about it and there's some value to it, people are sticking GPS sensors in them. Now, this is what I said looking forward. This is the only ugly chart that I'm going to give you lots of ugly charts, but this is an ugly chart I grabbed, and I hate when they do this stuff, but you've got multiple things on this chart here. You've got sales, units, and average selling price, ASP. So you can see from 2010 to 2020, this is F means they're looking forward, so this chart's a little old, but the data's still good. As they say, sales are basically relatively flat. The units are skyrocketing, and then the average sale price is going down. Now, you have to be careful with these charts. They're taking it across the whole spectrum, and there's a whole bunch of really cheap sensors. And the cheap sensors they're not really of interest, at least today, to talk about. But in general, what you see is that across the line, you see sensor prices coming down. We saw with the GPS things, several $1,000s down to $10. So my point here is you will see sensor data. It is coming on. I call it the rise of the sensors is the title of this talk. The number of sensor applications I see from our customers, almost every one of the new applications that customers are deploying with are all based on sensor data. Two to 3 years ago, it was less than half, right? So this is a big deal coming, and I see no end to this. Now, just to get a little background, event data. And event data is something that occurs asynchronously. So you can see it's random. You can't predict the time. Something occurs. The fan stopped. You drove into a tree, right? And you crashed, right? There's an event, not a good one, right? But it's something you can't plan on. It is asynchronous, and there's no deterministic relationship between the arrival of the data. The data just arrives. Sometimes you just ask for it, but it's not a stream of data. It's something like, what is the temperature now? And you don't look at it. Even though temperature does vary continuously, you can convert that. Now, Streaming data, you get continuous flow. The GPS receivers are streaming data. Where's my location? You get longitude, and altitude. You get a stream of that constantly. You will overwhelm you. So one of the things you end up as a data scientist doing is trying to figure out you can't store and process all the streaming data. A lot of it because there is no value in numbers that don't change, or you can't find a value, or in some cases in your application, it's not economically feasible. So there is still a lot of work to look at how do you reduce it. You can do things like you can compress data. You can do what's called time slotting. Basically, it says, heck, the sensor value today, right now, at this time slice, and it's uniform and consistent, and you got a sampling interview. The value hasn't changed, so why bother reporting it? So you can time collapse things down and say, for the last 1,000 seconds, the value's been this number, and there's no point in sending each individual value. Because one of the constraints we're going to have to deal with is remote systems is the communication path can be slow and expensive, especially compared to the sensors, okay? Now, let's build it. So we have a bunch of systems, and we're going to talk system architecture now. So now we're going to take a look. Remember, so you have to scale. So we got more than just one sensor. So here we have a series of sensors. They're all out there. They're all got a little bit of compute, and then we have a little bit of storage, which means you can do data science in that subsystem. You have a back-end system, so we got an edge sensor and we have the back-end. So you're going to hear me talk about edge computing or edge data science versus back-end data science. So one of the things is you got the back-end computer, which is going to have data which is sent to it from all these sensors. So all these sensors here, these guys are going to send data. One of the decisions we're going to have to make is what data, how much. And a lot of that's going to depend on what is in the middle. A lot of these remote sensings, they use Wi-Fi, they use cellular, they use satellite. Sometimes they're wired. But the fan-in, notice that all the sensors are fanning into the one system. You not only have to worry about the bandwidth or the data path here, you got to worry about, can this endpoint over here accept all the data flows? So when you do a system engineering approach, this is part of your equation. Can I absorb the raw data from all the sensors at the server? Can I afford in my solution to build a server big enough? Let's for an example. Apple's got a system that's 300 cabinets or 300 nodes. It's about quarter of an acre in size, right? These kinds of systems will cost you $120 million, right? So you have to look at how much data flow can you go to the back end to do the solution. So you end up, in a lot of cases, doing the data science at the sensor. And we're going to show you a couple of cool examples of that, because that doesn't necessarily mean that it's not a cool solution. And the other cases is we'll see cases where sensors at the edge talk to each other. And they communicate with each other because they can't necessarily get all the data back, but sometimes it may be the only way to solve the problem. Now, here's a case of using GPS data. Let's go to geofence, and you probably all use this. And what you do is you write a function that describes from those points, you end up creating a fence described by the points there that says when the GPS coordinates pass over the edge of that, create an event. So I've converted a stream of data to an event data. You can do this either at the edge. You can tell the device, send me an event when you pass the edge. Or you can send the data back and apply the algorithm at the back end. Early cases of this, they tried to send everything to the back end and it was slow. You couldn't process all the data. The problem you end up with is, are you going to allow and create a system where you can push a geofence down to a sensor? And we're going to talk an example where this is actually the case, because some sensors have their own built-in geofences, and how they operate will depend on where they are inside the geofence or outside of it. And I'm going to talk about geosensing locks, but we'll talk a little bit about that. Okay, cameras are the coolest thing. Cameras are the hardest thing. Cameras are still bleeding edge in a lot of cases. Cameras, to be effective, have the camera electronics. and they have a GPU or processing. You're going to see more and more of this done at the edge, but there's also some large data flows that come out of these things because they produce an inordinate amount of data. An 4K HD video basically is 3840 array by 2160. There's 8.13 million pixels generated every 60 times a second. And it's a large amount of data. You cannot raw send that anywhere. So even if you're watching videos, you're compressing it looking at pixel changes, you're doing something to the image to do that. So their cameras today are always tied with something compute line. Now that's a small NVIDIA GPU chip board, and it's about a couple $100, retail of one. So the prices and the technology is making the ability to do processing on that raw data at the edge even more viable. Now, very high data rates. Complex data streams. You can pull all kinds of cool things out of a video image. And you can do all kinds of cool things that in many cases you can use to replace all different kinds of sensors. So for example, I'm moving across the floor. You could actually put a sensor in me, wire me up and see that, oh look, he's walking across the floor. Or better yet, you can have a camera looking at me and seeing me walking across the floor where you don't have to wire me up. So some of the applications, early applications we saw, especially with doing motion capture, we'll talk about motion capture today, required sensors on you, but now it's getting replaced because sensors can be, physical sensors that can be intrusive, though they may be cost effective. As this technology increases and the cost goes down, you're going to see more of it. Now, there's an awful lot of engineering work that goes on in edge processing. It's a combination of the engineer working with the data scientist. So in these cases, you've got a specialist to design the hardware system that's going to either be also a data scientist, like some of you could be engineers being a data scientist or whatever area you're in, or you're a data scientist that knows something about that and you're going to work with a specialist, but you're going to work at that. Let's give you an example. So here's a very simple example. You can get this on a $300 camera you buy today. So what I do here is I define a series of pixels just like the geofence that says if there's anything that moves across this set of pixels, because I'm picking an area in the screen over here, I'm defining an area in those pixels across here, which is that line there, that says if there's a major pixel changes around that area, I'm going to make it as a virtual tripwire. So if a car goes by, passes through that tripwire, changes those pixels, an event triggers saying somebody just drove up your driveway. This you can buy for $200 today. 10 years ago, you couldn't even touch this thing. All right? So this is a perfect example. A whole bunch of people did an awful lot of stuff, especially data scientists on there, to work in the algorithms to put this, and they mass produce it, drive the cost down. Okay, let's talk about primitive data. Let's talk about some real solutions now. So let's talk about market basket data. So this is the very, very first thing that I ever saw with data science. And so what you're going to see here, it's not the fact that it's a crude sensor. I'm going to show you the data science of what we did to work around the fact that we didn't have anything but crude sensors. And so how did we get some more data out of it? So you look at this market basket, and that's what the receipt you get out of a store, whether it's online or whatever, or in a physical store, is called a market basket, and it lists all the products you bought. Those funky numbers are the UPCs, right? Remember we talked about UPCs, which uniquely identifies every product. It's a global standard, so every product has a unique UPC. So it defines that, and it says the cost. It looks up in the database, and it says, okay, here's my cost for this product, and it creates a market basket. And actually, in the database, you actually look at something like this. You see a transaction, what customer you were, the SKUs you bought, which is which is also the same thing as the UPC, the name of a product, how many you bought, the price, the cost. So you can automatically calculate how much margin you made on it, and what date it was. So this is a real straightforward. This is very simple database work. Not a lot to it. There's all kinds of obvious, simple things you can do with this. The inventories, what's coming in, what's going out. Do I have to replenish? Do I have to make an order? All this stuff is automated and it's been solved for 15 years. So there's not an awful lot of cool new things to do, but this is business is required. And whether it's an e-commerce company or a retail, they still have the same concept of a market basket. But what are other things you can find in this data? Well, if you take a look at the card data, and you take a look, or the the valued customer card or the loyalty credit cards, you can start to plot market baskets about where they live and try and figure out, is there any geographical significance to where they live to how much money I make or how much they buy. In this case, I look at this chart. This is a real chart, for example, real data. I'm going, I don't really see any big trends here. But let me give you another simple trend, and I don't have a chart for this. Let's say I have a product, and it sells a certain amount, and all of a sudden I see, for the last 2 months, a spike up in cost. On that cost, the number of products sold. And you go, And you say, why is this product selling? Was there a campaign? Is it the new hot toy? Is it some sweater that everybody likes that they saw on some social media site? Everybody's got to have one. And you start digging into this is a real example. You start digging and you go, there's nothing. This is a cold medicine. So when they started looking at it, and they looked at it and said, well, why are these spiking? So they went back and they started to pull some data from the CDC. They also noticed that, it seems to kind of correlate with the increase in flu symptoms. Now, that drug in this case was Theraflu. And by looking at the rise of the sales versus the reported incidence of the flu, the company realized that they were able to see the rise in flu cases before the CDC does. So that specific company, in this case it's Walmart, actually sends the data to the government saying, we're seeing an increase of this because people, when they start to feel sick, they go buy an over-the-counter medicine first before they go see their doctor, and they can use that to actually predict when flu is breaking out, and they plot it on maps, and they can say, look, we can watch the flu spread before the government knows about it because doctors lag. So they get an early indication from the sales of medicine from that. Okay, now here's another case. So you get a floor, and here's a floor plan of a store. Where do you put things? Is there a rhyme to reason why you have the bakery goods and the deli and the frozen food on the outer edges, and you come in here, and what is that stuff that you put at the checkout stand, right? So the goal here in the floor planning is to encourage customers to buy products with high margin. So they control everything, right? Remember, this is old time, so we just have market basket data to look at. So the goal is to increase, one thing is to increase impulse buy. So one of the things you do is you put dairy, meat, and other kinds of things that people buy on a much more regular basis. This is knowing the business. You put that at the back of the store. You force them to walk through the store because they're going to come to the store to buy meat and dairy and other kinds of things because their perishable lifetime is only a few days in a lot of cases. So you say, if they walk past the product, they may buy it. You're looking for that impulse buy, right? The other thing is they control the number of people at the checkout lanes. Why? Because they got the candy and the things you're kind of buying in impulse. So if the lane is too short and you zip right through, you're not going to get the impulse buy. But if the line is too long, you're going to get pissed off and not want to come back to the store. So that the number of lines and stuff is controlled. If they see the lines getting too long, they'll increase the people there, but they don't want to make them too short where you zip through unless it's waking hour because you're never going to make an impulse buy. The percentage goes down. Now, they do this analysis, they do it on a store basis, and they look, because every store in different parts of the country has different buying patterns. You buy different things in Florida than you do in Alaska, right? But, you're not going to be buying the Ugg boot, the gigantic, subtropic coats in Florida in the summertime. So there is significant, but the other thing is, where do you, so now that we know you want to put those things in the back, where do you put things on shelves and things on the aisle? So there's a margin business here. And the thing that it is that when you buy something, and this is where it's going to vary by area depending on their average height, is people tend to buy things first they see at eye level. And then as you go down the shelf, you tend to buy it less. And they've studied this. This is understanding the business and the psychology. The psychology is you look at the eye level and you say, I'm going to buy that product. So the data scientists work with these algorithms, and they also NCAPs are a great way. So they work with this to figure out the proper placement. Many of the retailers rent the shelf space. So they use, if I own, Duncan Hines, Pillsbury cake mixes there, right? I would rent those shelves, and the eye level shelf's going to cost more than the shelf at the bottom of the rack. So I want to put the things on that shelf that gets me the largest margin because I'm trying to maximize my profit for the area shelf because I'm paying the retailer for that shelf space. Not all retailers do that, but when you do that, you'll spot it. You'll see a brand in a block. So in this case, what you see is you see a block of cake mixes all by one company. And that's a clear indication that this is a rental case because they usually will rent all the shelves. If you really you got a lot of money, you would just rent the high rent space. And of course, everybody pays for end caps because end caps typically has one product from one manufacturer, and they pay for that. Because people go around the end cap and you get to look at it from 270 degrees. And you're walking around it, you go, hot damn, I really want one of these things, right? So the psychology is important. So understanding the business is, you have to end up coding this into your solution. Now, what else do you know? Where do I put things on the floor? I keep asking about that. Well, I don't know where people walk, but I do. I know the market basket. I know what you bought. So this was before video cameras, right? I can create probabilities of the paths you had to have walked through the store based on what you bought. And if you do that for all the market baskets, and you look at all the different combinations, you throw out a lot of ridiculous paths where you just, jump up and down. Most people are, trying to get through supermarkets in a reasonable time. There's often a pattern where you go up and down an aisle and walk out the box. But if you do this for all market baskets, you end up with this is a heat map. And this is a heat map of a real storage and a market basket data. And you can see the stuff at certain aisles depending on what was there, and I have no idea what it was for this heat map, what was in those aisles, but you can generate, the products in those aisles were generating a lot more foot traffic than anything else, so the retailer may move things around or charge a premium for these people to be near each other to the manufacturers. Again, business and data science. Okay, let's move on. Let's go to something a little more interesting. Or maybe I'm an engineer, so I always like trains. This is a bad thing to happen. Train derails. Why? Well, one of the most common things besides speeding is that. That's where a bearing seized in a rail car wheel, and the bearing wore out. It seizes, you get this fire, the wheel starts to skid, it gets resistance, the train pulls on the track, and poof, you end up with that mess. How do you fix it? You got really old trains. Trains are really expensive. Most trains have been out there 40, 50 years. The cars, you have a real problem. Now, you can look at this and say, So what they found is that the temperature of the bearings and the wheels are a clear indicator of the fact that you're going to have this situation. So that what you want to do is you want to be able to get sensors, infrared heat sensors, they're not that expensive, to measure the temperatures of the bearings and in the wheels. Now, in new trains, it's easy. They build it in. So what you see here on the left side is you see here's the transmission box, and here's the sensors in the end. You do the wheel bearings, and sometimes they'll also measure the wheels. And they have an inboard computing system, and they go for every carriage, and they all look at this. So as it's going around the tracks, again, wheel bearing temperature will vary over time. If you're making a turn on a cone, you're putting more pressure, you'll put more lateral pressure on the bearing, so you get temperature rises. So what you have to so the data science isn't obvious that, it gets hotter, that it's a failing bearing. You have to take into account where it's traveling. But what do you do for old trains? For old trains, what you do is you put sensors in the track at periodic locations as the train passes by. You have sensors looking up that grab the temperature off the bearings and the wheels and send that data back. Okay? So a real customer did this, right? Tulsa or Omaha, if you look up what railroad is located in Omaha, you can talk about it. But they have sensors periodically put in specific places of the tracks. As the trains go over, they capture the readings and they send the data back. So this is the case there really wasn't a lot of data. So it was an easy thing to do a back-end process because what they really wanted to do was to do a lot of algorithms on the data to try and figure out, is this bearing going to fail? Because they don't want to be changing bearings too early because it's expensive and because the train that car will go out of service. But if they wait too late, they have an insurance problem or even a fatality problem, so they want to avoid that. So this company employed, it didn't cost them much to do it. It cost them about $20 million. They reduced derailments by 75%. So a whole crew of data scientists worked on that, trying to look at the temperature data, worked with the engineers who worked on the bearing systems to figure out when was the right time to make the change. Okay, big old mine. How do you know what paths to put in the mine? I mean, obviously you're looking for ore. Maybe it's the sand mine, but you got all those paths, and you look at those little things there. There are these things, these gigantic trucks. These things are ungodly expensive. In fact, it's the world's largest truck, right? It's a Cat 797. It's got 4,000 horsepower. It has a 1,000-gallon fuel tank, and it carries its gross weight when it's filled is 1,375,000 pounds. This thing costs at least $5 million. You don't want it idle. If it's idle, it's not making money. It's not making money. You are not making your profit. You want this thing busy all the time. You also don't want it to fail. It's got 124 sensors. So one mine, I picked one mine. Each of these trucks has 124 sensors. There are 331 of these trucks there. They run 724, 7 days a week, 365 days a year. You do not want your trucks idle. You don't have trucks sitting around because they're an asset that's not generating any money. So they got sensors everywhere. This is the case of really dumb primitive sensors. So there was a lot of work throwing out crappy sensor data here. But you get all these sensors from all the things, including GPS, gas mileage, and everything, and you create an event stream. And this is a sensed event stream that you're creating. And you're doing a lot of compression because at the time, what this is being done is this one is being captured in the truck itself and dumped out at nighttime. So there's not a real communication. So they did a local capture because at the time this was done, the technology really wasn't there for doing this with a remote communication. So you end up with event streams that look like this: daytime, vehicle ID, GPS location, and a sum of all the sensors. And there was a whole bunch of sensors, and you get this periodic stream. So you plot this on a map, and you say, what the heck, where is the truck, where is it going? And you plot with these different colors. And the colors is it was running really slow. The green was going pretty quick. So this is the case you're looking speed, but you look at, there's all kinds of inputs that they're looking at, looking for value for this. This typical application found a whole bunch of really interesting things to improve cost, but one thing I picked out of all their solutions was idle time. They looked at the analysis and they realized the way the trucks are being routed, the speeds they were going, where they were picking up, how they were maneuvering the trucks around was wrong. They were idle 625 hours a month for the trucks for that fleet were sitting around doing nothing. So they used the data from the GPS and all the location data, and what they did is they got that down to 161 hours a year. This was another, $100 million plus savings per year. That's every year. So this is another case of doing the sensor data. How are we doing on time? Oh, we got plenty of time. Let's talk about connected cars. So this is a hot new thing. All cars, not only the cars have full electronics, you see Tesla, you see GM doing this. They've got computers up the wazoo in the car. There are sensors everywhere. So all these sensor systems have a primary value. So we're going to look at not the primary value for the sensor, but for the secondary value you can get from the sensor. Because what you're trying to do is dig some value out of it. So a lot of these sensors we'll talk about in a minute, some of them are what are called a closed-loop system, where the sensor is actually part of the solution. Maybe to give me an example. I'm walking down this way, and I look at this lectern thing, and I go, if I keep walking, I'm going to hit this thing. I better walk this way, so I walk around it. So my eyes as a sensor looked at that and said, if I don't change my course, I'm going to hit that thing, so I did it. So my sensing, it was part of the system, I realized I have to make a change. So that's a closed-loop sensing system. If I look and go, oh my God, there's a lectern in the way, and I overreact, and I walk over here, and I walk, and I impale myself on this metal thing, my eyes are all screwed up, and I need to go get new glasses, which is probably true. So you see this in a lot of cases of automated steering systems. The early ones had problems when they saw something in the road, they overcompensated. That's data science working on it. So we're going to look at all these sensors. We're going to look at two. We're going to look at the entertainment system and look at the active suspension system. Okay, so there are 33, the case study for this company, there's 33 million of these cars on the road. They all have cellular data connections back to the corporation. They send the data in packets every 15 seconds. It's a low data rate because it's cellular data. There's 33 million cars. So there's an awful lot of data gets generated every day. You send about, each packet has about 1 kilobyte of data in it. So times 33 million times, average car is, probably doing about 3-4 hours or maybe 5 hours a week of traveling on average. So you end up with something that's terabytes in data size pretty quickly. So we're going to take a look at two systems. We're going to look at the entertainment system, and we're going to take a look at the active suspension system. So here's the typical entertainment system. And, you got dials on it, you got buttons, and it does a whole bunch of things. It's got, navigation system. You can stream data to. You listen to the radio. I had to put a block diagram on. You can't get the E out of me. But anyway, this is the block diagram of this radio. And the interesting thing here, let's build this out here, is in this thing we have the sensors, which is the touchscreen display here. We also are not shown. There's somewhere here. There's some dials, some of the digital dials that are encoded. Those are also going in there. And you also have GPS is also in this part of the system, and you also have the cell connection for out of this system as well. So this is where the call home features are. So inside the car, all these sensors all these computers with sensors are wired on a network, and so all the sensors are capable of having data sent through this communication system using cellular data, sending it to the back end. So obviously, there's not a lot of data science here for doing the most operations on you're changing stations. It's mostly computer science. Changing stations, you listen to music, changing sources. There's really not a lot. But let's step back and say, well, what else can I use with that data? How can I make money on it to subsidize the cost of this hardware? Well, here's something. If you look at radio listeners, and you look at it and you say, 54% of people that listen to the radio listen only in the car. So that's a very large percentage of the population's radio listening time is in one location. It's in a car. And it varies by age. It says 62% of you guys are listening to in the car, and 46 of me are listening to the car. And I'm going to say, I tell you, the only time I ever listen to the radio is in the car, and otherwise I never listen to it. I hate commercials, and even if I stream data in the car, I don't do a lot of that. So anyway, so this is the demographic. So there's some value here. So somebody's sitting there going, okay, we have an environment where we know something about this consumer. They're listening to the radio in the car. Well, what is in the radio business? Well, they have these hit charts. And what it is, record company goals is they want to get hit songs, they want to get the maximum spin time or the maximum airplay, because if the song becomes popular, the band goes to concerts, they sell record downloads, they sell tickets and shirts and all kinds of other junk for very popular things. If the song is popular, they want as many people to hear it because they want the biggest airtime for a popular song. They're growing that group. Radio stations love hit songs too, because people listening to their radio station because they like the songs they hear, or they listen to that streaming media. They like the way the DJ is setting things up. They get increased ad revenues from both because more people are listening, they're listening longer, and they get more people listen. The combination means when they have an ad, they can charge more because, hey, I've got 100,000 listeners and this radio station's only got 1,000, so I get to charge more. And it's the demographics you like. So you can see, there's a business case. So the goal here is you want to be playing hit songs, and when the song is no longer a hit song, you want to reach in your back pocket, grab out the next potential hit song, throw it into the mix and say, okay, it's now time to try this and see if we get some airtime in this. How do you know when it's a hit song and when it's not a hit song? What they did in the past is they did surveys. They surveyed people and said, do you like the song? They went to record stores, which they basically don't exist, and said, who's buying the records or the CDs? You can't do that now, right? So the question is, the question is, since people are in a car and they're in this medium, when is the song a hit and when is the song becoming a dud? When is it being listened to and people like it? When people are tired of it and don't want to listen to it anymore and we got to get rid of it? So let's go back to the radio. User selects a radio station or a streaming source. The song names, etc., are embedded in the stream, or you can figure this out from the time and what station you're listening to. So don't worry about that. So you basically know what song is being listened to. A decreased interest event is one of the following. Oh, crap, I hate that song. It's country western. Yuck, right? Let's switch source. Right? You change the radio, you listen to some of the media, you change the radio station. You lower the volume or you push mute because you like the station, you just hate the song, you just pray for it to get over with. So those are events, operations in the system that says you have decreased interest. Increased interest, basically, one primary thing is you turn up the volume. It means, oh, you like it, or you leave it on. You leave it on is like you're still interested in it, but the clear indication that this thing is rocking is people turn up the volume and start rocking out to the music. So these are interest events. So they get generated, they get picked up, they do edge processing. This is done in the communication system, looking at the data stream, looking at the controls and saying, huh, it's one of these interest things. They like this thing, so I'm going to send this data to the back end. And they're going to use this, then they sell the data to the record companies who now know, then when they work with their radio stations, of what to change their song rotations based on the fact that they get a very large sample of understanding what data is hit data, what is record songs are hit songs, and which ones are not. So let's look at car suspension. I'm going quickly because I don't want you guys to get bored. Here's a car suspension system, and I'm going to point at the strut, or the damper, or the shock absorber. You give multiple different names. That's this thing here, right? So if you're in physics, you know at the point of the strut damper is a couple fold. Mostly is to keep the springs from oscillating. The goal of that is to keep the tire on the road. Now, modern struts, you can change the viscosity of the fluid inside the strut. So you can change the rate at which you can move the resistance to moving dynamically on the fly. And it uses magneto-resistive fluid, and you pump a current through there and you change the viscosity. So you have these holes drilled inside. There's a piston in there. If these holes drill in there, if the liquid is very viscous, it drains slowly, so it's really hard to push down. So they use it if you're falling in a ditch or something. They use it to damp it so the springs don't oscillate. And it's a very important part of controlling, keeping the goal of this system is to keep the tire on the road. Now so this is a closed loop system. It's measuring the fact of whether the tire's on the road. How does it know the tire is on the road? Well, a couple things. It can look at the fact that suddenly the damper position moves, and they can measure in inches up and down that this damper goes up and down. They go, oh, okay, the wheel is moving up and down. There's other indications that the system's way more complicated. Is the wheel spinning? Is it a powered wheel, and is it spinning? If it's a powered wheel and spinning, it's not touching the ground, right? So this is not good. So we have to maybe adjust to try and get it there. Or it's not a powered wheel, and it's slowing down. Another indication it's probably not touching the ground, right? So remember, powered wheels, if you pull them in the air, they're going to spin wildly. So that is all part of a control system. So when you go around corners and stuff, there's a main control system, closed loop, just like me walking into this thing, making the adjustments saying, I'm going to make all these algorithms to make sure the car is planted. This area has been running, they've been doing this for 20 years, a lot of very sophisticated algorithms. Closed control systems are really interesting. If you ever are interested in this kind of stuff, there are courses here at UCSD that talk about control systems. It's often given in mechanical engineering, and it's very generic, but they can go. But it's also a case where so many systems now are computer controls, closed loop control systems, that it's worth studying for. I find that I'm running into more and more of these things, and we just recently had a project at work where we had to do a closed loop feedback system in software, and a lot of the engineers didn't know what I was talking about, so we ended up having to do a little bit of a tutorial on this kind of stuff. It's really fascinating, but there's a lot of math here, so if you love math, this is a really cool place. So anyway, I get off topic. So we have the strut sensor data. What else can you learn from it? Well, here's a car. Look what happened to the car. It just fell into a ditch. And you can model the ditch, and this is the case basically with the tire is you're going to see a change in the direction, and mostly it's an acceleration in this axis going down. The wheel all of a sudden goes whoosh as you fall into a ditch. How far it accelerates depends on the size of the ditch and how you hit the ditch. Did you hit the ditch on the side? Did you hit the ditch in the center? Or whatever. And how big is your wheel? If you got a gigantic wheel in a little ditch, you don't even notice it. But if you got a little wheel in a big ditch, you break your axle. So one of the things is you can take this data and you can tap off the control system data, which is they do. So the system's running and the dampers are running, and they put a T-fitting, that's like a water fitting on the side of the data stream for the dampers, and they go, hey, damper, where are you moving? And they look at that and they put an algorithm and they say, when we see that pattern, and this is acceleration, so when you see hitting the edge, you accelerate, you go up the edge, you hit the edge, and often there's a lip on this thing, you hit this lip, and then you see the acceleration in the other direction, so you're dropping down this way. That is a unique pattern that describes a pothole. Now, there's all different kinds of potholes. So part of the project here for doing this stuff was data scientists work with engineers, and they were doing test trials to try and find the algorithm that looks at the movement data of the damper to say it's a pothole. So now you take the pothole, and you've got a GPS in the car, and you know which wheel hit the pothole, and you know the GPS location, so you can calculate the distance from the wheel, from the GPS transmitter, because it's going to give you the location there, where the antenna is. You can calculate that distance. You also know the width of the tire, and you know the distance there, because the type of the car will tell you approximate width of the tire, both the width and the radius. So you have an idea to calibrate from that information how bad the pothole is. So if you look at what's going on the road, you got these couple cars, and you take a look at that truck over there. I guess it's a truck up there. And if you have a pothole there, and you can see it passed right over that blue line. That truck passed right over the center of that pothole. And the truck coming behind it, that big tractor-trailer truck there, his wheel spacing is different. It's going to hit the edge. So what you're doing here is you do the edge processing in the car to say, I spotted a pothole, because you certainly don't want to send the dampers data there. Damper data updates 60 times a second, okay? And it's a 64-bit value, so it's what, 8 bytes? So it's a lot of data flow. So you're doing a T-fitting, and you're creating an event from this. So you send this back, and you send back a date, a time, a vehicle ID, vehicle type, GPS location, and the information about the pothole itself. You send that back to the back end. The back-end gauge processes all the aggregated cars floating going on. So cars are going up and down this road, and as you get a certain number of cars doing this stuff, they basically map out the pothole. They know where the edges are, and they know approximately how deep it is based on, it's a tractor-trailer went over the same spot, barely saw it. Okay, we know its diameter of its wheel, so we can get an idea of how wide the truck is. Oh my God, the Honda Civic went over there and broke its axle. We tow it away. Right, so we know that it's a fairly deep thing, but it's not a very large pothole. So this data is being collected, and it's made available to cities free of charge, well, just for actually data transfer costs, which is basically free of charge to go fix your potholes. Because it accurately knows within a couple inches of where the pothole is. So this is a program that's running, it's not running in San Diego, but it's running in some other cities, and they're actually using, this manufacturer is actually sending the data to the cities so they can fix the pothole. Other companies, this is Land Rover, what they're doing is that was using an existing sensor. What they're trying to do, looking forward, and this is one of the rare slides I'm looking forward, is they're actually using different kinds of LiDAR sensors. Sometimes they use lasers, sometimes they use other kinds of ultrasonic, but they're using cameras, and they're trying to find the potholes, not sell the data back necessarily to the cities, but to predict them, to tell you you're going to hit one before you hit there so you don't break your axle, break your wheel, or whatever. I can't tell you how many times in the past year I've had to change a bent wheel on my car all the time because literally the rim gets bent because I run into a gigantic pothole somewhere because I probably drive way too fast, but that's another story. Now we're getting to more, this stuff is real, now this system's been out just a couple years. So this is motion capture. This is motion capture in a basketball court. And the basketball courts are kind of cool. They're fixed size, great lighting, very expensive players. limited number of players and a fairly relatively straightforward gameplay. So they do motion capture by looking at the images. So they actually watch the players, where they move, they graph it out, they capture where the ball goes, and they collect all this data, and there's no sensors on the players to do this. They do it entirely with video cameras. Pretty expensive thing to do. This is Utah Jazz, by the way, that does this. They're trying to do it in hockey as well, but hockey guys don't, it's not a lucrative sport as basketball, so you don't see that, but this is some of the early work that the New York Rangers are starting to do for actually studying where their players are, but they're nowhere near advanced. Now, the Utah Jazz, they use it to look at where they start plotting where the shots were taking, who was in front of the opposing player at the time, where's their angles, what was their percentage scoring against different opponents in different spots of the courts, and they start plotting the data, and they do this real time during the game. They also do it at training, but they do it real time during the game, and they use it during the game to change strategy. So the coach is going, he's not making the shots. This guy's good for these shots. When he's going against this person in this spot, he's getting blocked out. Move him. Have him use something else. And so this is continuously going on. This is getting more and more sophisticated. Right now they're doing position of the players and the balls. They're starting to do rotation and vertical direction. They don't have that down yet, but that's what they're working on now, is actually trying to map how the players rotate and how that impacts the shots. And that's something they're starting to do now with the next wave of the sensors coming out. And they create these playbooks from this. Real time. They made a difference. They spent a fortune on this, and they are definitely saying that this is making a difference in gameplay. Now, we're going to talk about container shipping. This is if there's one industry that has more data scientists working on it than any other, it's this one, because the problems are so widespread and the money is so large. This is the case where I said, this is Maersk, where they spend $16 billion a year minimum on fuel costs. So everything is expensive. So the container industry, there's a standardized container. It goes from one port, it's put in a truck, it lands on an ocean vehicle, it's transported to another port, it gets moved around, it gets picked up, stuck in a truck, and ends up delivered. All kinds of problems. Routing problems. Security. I want to know if somebody breaks into my container. Even if they got the key, I only want them to be able to open the container up when they're at the source or at the destination. Even if they have the key in the middle, they're not supposed to open the container up. So we'll talk about a little bit about geofencing there. But this is a big industry. Now, you see the ships, you see them loading, and you see the same container going into a dock. Now, why am I so excited about this? This is the problem that sat on the shelf for 8 years. It was deployed about 4 years ago. Sat for 8 years because they couldn't do the technology. There's the ship. It's 18,000 containers on it. The height from where the containers are inside the ship, from here to here at the top, is 18 stories. That's 2 to 3 times bigger than the tallest building on campus. This is 18,000 containers in one ship, right? So you got a little bit of problem there. You got to track the contents of 18. So you got these containers. Here's a picture we took from on the side. That's looking down the hole. That's the outside. There's the water. There's the hole. There's looking down the hole. You can see some containers on the side. Everything from where you were visible down is inside the hole, and everything's above. So that's like 8 to 10 stories looking down. Believe me, if you don't have vertigo, you will. These things are immense. Okay? So a container is pretty big. There's the 20 and 40-foot containers. And they have this thing called a reefer container. No, it is not a marijuana joint or whatever it's called, right? So a reefer basically is a refrigerated unit, and it's stacked full of sensors. It's got temperature, humidity sensors. It's got, all throughout, because it's trying to make sure, because of safety, that every part of every piece of food in that container is in the proper temperature, humidity, and protected. There's shock and vibration sensors. Each of these containers have Wi-Fi, cellular, and satellite. So no matter whether they're on a ship or they're on land, they can phone home. They have all 3 mechanisms. They have global telephone system so it works anywhere in the world. These are worldwide shippers. They go everywhere. They have these things called geofence locks. Remember we talked about geofence, right? You can't, so the way the locks work is once the lock is put on the container at the shipping point, the lock looks at where it is and says, oh, you got the key. Nope, I'm not opening. So you have to cut into it. And if you start cutting into it, the vibration and heat sensors start screaming, and it will start to transmit across all possible radio spectrum saying somebody's trying to break into me. So the new things is the bad guys come up and they try to do broad spectrum jamming. They try to go and sneak into the ports, try to jam all this stuff. Some containers spot this, and the data scientists in there says, oh, look, somebody's jamming over there. They haven't got me yet. They start screaming. So the whole point here is trying to take advantage, and this is all data science at the edge. So you got this problem here. So Maersk at any point in time has 300,000 containers at sea. That's a lot of things. They generate, each ship has about 2,800 sensors, independent of the 18,000 sensors in the containers. And they generate about 30 terabytes a month, which is a fair amount of data, right? So you've got this problem. So what you end up seeing is the containers, because they're at sea, they can't get the cell phones. What they often will do is they'll transmit to a receiving or cell station that's local. So they actually have their own little phone cell stations on the ships. And the ships will send it back to satellite. Some of the containers are also capable of sending up to the satellite directly. So you have all the containers talking to the ship. So the guys, you think about what's going on. You got this 18-story high things and it's end wide. And then when there's a fire in a container in the middle of the ship. You kind of want to know about it. Now, there's not a lot you can do because you can't move it, but the containers are designed so this fire will snuff itself out because most of them are airtight. But at least you know there's something the hell going on in the middle of the ship. Now, as an aside, all this other data is used for stacking ships, and of course, there's a whole logistics about putting containers on ship, and if you stack them wrong, ships keel over and all that kind of stuff. But we don't have time to talk about that. But anyway, you've got this problem. You got 18,000 containers. They all want to talk to home. The problem is, if you look at it, you look at that. They're all spread through the ships. That's a smaller ship, but has a cutaway. You got these containers that are buried in the center. They don't see air. Metal block signals. They can't talk. But how do they work? Well, they create an internal mesh. So when the containers fire up and they're running, they go, oh, hell, I can't see a satellite. I can't see a Wi-Fi signal. I can't see a cellular net, but I can see my buddy. And each guy does this, and they map out among themselves a mesh, and they figure out who the hell's on the edge. And they send all the data to him. So they're sitting there going, I don't see it, I don't see it, he sees it, he forwards the data out. Same thing happens all the way over here. So this has to be automatic because you think about this. You can't program it this way because you get to a port, you pull off all the containers, you put the ones down that you want to leave at the port and you put them back. And also sometimes you're adding empties because you can't just put all the containers for that port at the top because you create ships that are top heavy and they keel over, so you have to be careful about that. So the systems, so they have these sensors, they create this automatic mesh. This is why it took 8 years, by the way. And they have all the sensors inside, specifically the reefers, inside the same communication mechanisms using RFID or other mechanisms, RFID at the minimum, or small Wi-Fi cells inside of it to pick up all the sensors that are inside the container. And so you create this dynamic mesh communication network. This is the coolest thing. It really works. And because you go to a port and you got a bunch of longshoremen whipping the containers around, slopping them back down, and the system reconfigures every time it comes in and out of port. So that's a port. Those are those ships, right? You go, oh my God, look at all the containers. So the containers land at a port, they get plumped down the port, they get moved around, and vehicles roll up to the port to pull it up. Now there's a legal thing that goes on here, right? You got transfers at the port. So when it's on the ship, Maersk, for example, is responsible for the container. When it lands in the port, responsibility for the container transfers to the port authority. When the tractor trailer comes up, picks the container up, puts it on the truck and sends it off the port, UPS or whatever it is, they own responsibility. So you've got to know where it is. But on the other hand, the containers will move around the ports all the time. They'll be moving around, but they're not a transfer of ownership. So how would you solve the problem? You geofence it. So they create the geofences inside the sensors for that port, and they know where they are, and they go, I'm at this port, this is my geofence. So it knows where the GPS locations are where you would be at a berth, so I'm still on the ship. Now they know they're moved because they've got vibration sensors and acceleration sensors, know they're being picked up, but they have to cross the path because you're looking for change of ownership. When it lands on a dock and stuck on one of those lanes, whoop, pow. Event gets triggered, I pass from the orange geofence into the yellow into the orange, and now I'm on part of the port, and the port owns me. So if there's anything happens, and again, internally the locking mechanism going, I'm not at the end location, I'm not opening up. And again, they will protect themselves. And they notice they put the reefers, they stick the reefers up in this section here because reefers really they are usually the ones at the edge because you got to get power to them. It's really hard to get power to something that's buried inside the middle. So they tend to put the reefers at the edge. And they have this special section where they have power there. The rest of those things are just asphalt or concrete where they dump the containers at. So this is the coolest problem I've ever had the occasion to work on. I worked with them 8 or 9 years ago, and then I didn't work with this company, and I ran into the guy about 2 years ago at a convention, and he says, yeah, we finally implemented it, and he talked me through all the problems, and I was like, it was just fascinating how much it took to solve this. They actually contracted with the university, actually to work on the mesh networking in there. So we have a few minutes left, because we're done. I have other things we could talk about. I know I went really quick, but here's my goal. First of all, 1, you have to understand as a data scientist, you work in a business, unless you go to academia and become a researcher. But if you go into industry, you're going to work in a business. You have to learn the business. If you learn the business, you can get a lot of value and add it to the company and get really successful. These guys, the guy who did that, makes well in excess of $700,000 a year, right? Who works on this stuff, the chief data scientist of Maersk. So this is an important, very good, now, so the other thing is, sometimes you don't have to use a lot of data science to solve a problem. It's sometimes the very simple things. The radio station example makes a lot of money. Just understanding the play, it's just looking at simple, there's no real data science there, the fact that looking for the value in the data. So any questions? None whatsoever? Are you an easy group? I went so fast I just blew you away. Not so.
In terms of the optical tripwire you talked about,
yeah.
How does that optical camera know whether or not the non-tripped wire?
Okay, so what it does is you define a series of pixels across the screen, and you say if there's an edge that goes past it, like a car's going past the edge, and you see the change from the normal. So it creates an ambient normal background. And when it sees a background change and an edge passing, it says, aha, something's moving by. Because those kinds of models depend on the fact there's a steady state where nothing's moving. And they capture that as the baseline.
So how about if the light's moving because the sun's setting?
Yes, it gets harder. They can get fooled. The cheap ones get fooled. The other ones switch to infrared. And they use other technologies. But yeah, there's all kinds of opportunities to do it better with cheaper hardware. So if you're interested in that, good business to go into. Any other questions? Yeah.
Okay, on our fourth year in our data science program, taking ECE classes, would you recommend doing that?
If you're interested in doing data science with electrical systems, I'm really what's called a system architect, right? So I was an EE, computer scientist, and I ended up architecting big systems. But having an EE background, I can flip between all of them easily. As I said, don't give up the data science, because when I got in trouble, I always had to hire a mathematician to bail me out, right? So again, I goofed off on my math classes, and I paid for it. But, at that time, mathematicians weren't data science didn't exist, so it was fairly easy to get them, but nowadays it's a different story. If you're interested in closed-loop systems, go see the ECE department. They have some really cool stuff there. I was just over there a couple of weeks ago, and I was very impressed. They have a very good program. Any other questions? This could easily be a course. One of the things I've been toying with is actually making, not this, but actually making sensor technology a course. So that's something, if you're ever interested, I'm in HDS, I'm in I'm down a couple offices from Brad. Come by and see me, or send me email, but I'm ke.muller@ucc.edu. Come by and talk to me. Yeah.
Do you use Google search, and how do you feel about using Google products?
I mean, is it ethics thing? Yeah, one of the things it's hard, it's a hard one to hit. One of the things you always end up doing with some of these data science projects is, or these system projects, is you think about the ethics of it. I'm lucky. I've never been in a case where I worked on something that I scratched my head on. I tended to stick to things like, caterpillars, for trucks and shipping containers and stuff like that I avoid that stuff in. Yeah, there is ethics. You have to worry about if you're successful, can it be misused? So there's a whole set of class of data that you have to worry about. That's going to be I have trouble doing that, so I avoid it. I just go into cool things. I'm a hardware guy. I like hardware. Any other questions? You all want to go? Goodbye. Have a good time.